Chapter 2. Aerodynamics. Introduction. This chapter focuses on the aerodynamic fundamentals unique to weight shift control (WSC) operations. The portions of the Pilot's Handbook of Aeronautical Knowledge FAA-H-8083-5 on principles of flight and aerodynamics apply to WSC and are a prerequisite to reading this chapter. Aerodynamic terms. Airfoil is the term used for a surface on an aircraft that produces lift, typically the wing itself. Although many different airfoil designs exist, all airfoils produce lift in a similar manner. Camber refers to the curvature of a wing when looking at a cross-section. End of page 2-1. A wing possesses upper camber on its top surface and lower camber on its bottom surface. WSC airfoils can be single surface, with one piece of fabric for most of the airfoil, for slower wings. Faster airfoils have two surfaces and are called double surface wings, which are more like an airplane wing. Figure 2.1. This double surface allows the wing structure to be enclosed inside the wing, similar to an airplane wing, reducing drag and allowing for faster speeds for the same thrust. The leading edge is the forward edge of the airfoil, and the rear edge of the airfoil is called the trailing edge. The chord line is an imaginary straight line drawn from the leading edge to the trailing edge. The WSC airfoil typically uses a different camber with the airfoil high point farther forward than the airplane airfoil, creating a more stable airfoil. Figure 2.2. The WSC wing is a unique design of airfoils that differ throughout the wingspan. Looking at a top view of the wing, in the center is the wing root and on each end is the wingtip. Wing chord is any section of the wing parallel to the wing root. Figures 2.3 and 2-4. The wingtip chord is the chord where the trailing edge is furthest to the rear of the wing. This can be inboard of the tip, as shown, and can vary depending on the specific wing design. The nose angle is the angle made by the leading edges, typically ranging from 120 degrees to 130 degrees. Sweep is the angle measured between the quarter chord line of 25% chords, and a line perpendicular to the root chord. Figure 2.3. End of page 2-2. Looking at the rear view of the wing, anhedral is the angle the wings make angling down and dihedral is the angle the wings make angling up. Figure 2.5. Dihedral is the positive angle formed between the lateral axis of an airplane and a line which passes through the center of the wing. Anhedral is the similar negative angle. Wings with sweep have an effective dihedral characteristic that counteracts the physical anhedral to develop the required roll stability for the particular make/model design objective. This is explained in the Pilot's Handbook of Aeronautical Knowledge in much greater detail for further reference. Unlike airplanes which typically have significant dihedral as viewed from the front or back for roll stability, WSC wings typically have a slight amount of anhedral as shown in Figure 2.5. An effective dihedral, which is a characteristic of the swept wing design. Wing twist is the decrease in chord angle from the root to the tip chord, common to all WSC wings and ranging from 5 degrees to 15 degrees. This wing twist is also called washout as the wing decreases its angle of attack from root to tip. The term billow was originally used for the early Rogallo wings as the additional material in degrees that was added to the airframe to create the airfoil. It is still used today to define the amount of twist or washout in the wing. The WSC may not have twist/washout when sitting on the ground, and must be flying and developing lift to display the proper aerodynamic twist characteristic of WSC wings. Figure 2.6. The longitudinal axis is an imaginary line about which the aircraft rolls around its center of gravity, CG. It is also called the roll axis. The longitudinal axis is not necessarily a fixed line through the carriage because the roll axis changes for different flight configurations, but can be approximated by the middle of the propeller shaft for a properly designed WSC aircraft and is typically parallel with the flight path of the aircraft as shown in Figure 2.7. Angle of incidence is the angle formed by the root chord line of the wing and the longitudinal axis of the WSC aircraft. End of page 2-3. Unlike that of an airplane, the WSC angle of incidence has a significant change in flight because the carriage is attached to the wing, which allows the wing to rotate around the carriage hang point on the wing and is controlled by the pilot as shown in Figure 2.7. Pitch angle is the angle the WSC wing root chord, center of wing, makes with the Earth's horizontal plane. Many pilots confuse the pitch angle, which is easily seen and felt, with the angle of attack, AOA, which is not as perceptible. For example, if flying in a glide with the engine idle and the nose lowered, the pitch angle can be below the horizon. Another example would be flying at full power climb with the nose raised, resulting in the pitch angle being well above the horizon. Figure 2.8. Pitch angles are covered in greater detail in Chapter 6. Deck angle is the angle of the cart's wheel axles to the landing surfaces, as in the powered parachute, PPC. Deck angle. Relative wind is the direction of the airflow with respect to the wing. It is parallel to and opposite the WSC flight path. Relative wind may be affected by movement of the WSC through the air, as well as by all forms of unstable, disturbed air such as wind shear, thermals, and turbulence. End of page 2-4. When a WSC is flying through undisturbed air, the relative wind is parallel to and opposite the flight path. Figure 2.7. AOA is the angle between the relative wind and the wing chord line. Because of the wing twist, the AOA is greatest at the wing root and decreases along the wingspan to the tips. This is an important concept covered in the stability section of this chapter. For changing speeds during gliding, level flight, and climbs, AOA is the primary control for speed changes. Lower angles of attack produce higher speeds, and higher angles of attack result in slower speeds. The pilot changes the AOA by moving the control bar forward for high angles of attack and slow speeds as shown in Figure 2.7, top. For high angle of incidence in Figure 2.8, top. For high pitch angle. Low angles of attack for fast speeds are shown in Figure 2.7, bottom. For low angle of incidence in Figure 2.8, bottom. For low pitch angle. Most of the time, the pilot is flying at the cruise AOA, which is the trim position of the control bar, and the pilot is neither pushing out nor pulling in on the control bar. This trim position is the AOA and speed the aircraft flies if the pilot is flying straight and releases the control bar in calm air. Figure 2.9, middle. Planform is the shape or form of a wing as viewed from above. The WSC wing comes in a number of planforms ranging from the larger and slower wings to the smaller and faster wings. Aspect ratio is the wingspan divided by the average chord line. A WSC aircraft with a common 200 square foot training wing, about a 35-foot wingspan, and with a typical mean chord line of 7 feet, would have an average aspect ratio of 5. This relatively low aspect ratio is less efficient at producing lift. A higher performance wing with 140 square feet, a 35-foot wingspan, and an average 5-foot average chord would have an aspect ratio of 7. The WSC wing is similar to airplane wings in that the aspect ratio differs with the specific design mission for the aircraft. End of page 2-5. For the same wing area and similar design, the lower aspect ratio wings produce less lift and more drag, higher aspect ratio wings produce more lift, less drag, and may require more pilot effort to fly, depending on the design. Figure 2.10. Wing loading is a term associated with total weight being carried by the wing in relation to the size of the wing. It is the amount of load each square foot of the wing must support. Wing loading is found by dividing the total weight of the aircraft, in pounds, by the total area of the wing, in square feet. For example, the wing loading would be 5 pounds per square foot when 1,000 pounds total weight for a 2-seat WSC aircraft with 2 people is supported by a 200 square foot wing. If flying the same wing with 1 person and a lighter total weight of 500 pounds, the wing loading would be 2.5 pounds per square foot. In the small, high-performance wing of 140 square feet loaded at 1,000 pounds, wing loading would be 7.1 pounds per square foot. Gliding flight is flying in a descent with the engine at idle or shut off. For example, use a glide ratio of 5, which is 5 feet traveled horizontally for every foot descended vertically. Glide ratios vary significantly between models. WSC Wing Flexibility. The WSC wing retains its rigid airfoil shape due to rigid preformed ribs called battens, which are inserted from the root to the tip along the span of the wing, similar to ribs for an airplane wing, and a piece of foam or mylar running along the top side of the leading edge to the high point, which maintains its front part of the airfoil shape in between the battens. Figure 2.11. Some WSC double-surface wing designs use a rib similar to a PPC wing that attaches to the lower surface and the upper surface to maintain the wing camber in addition to the battens. Even though the airfoil sections are rigid, the WSC aircraft is called a flex wing for two reasons. First, it is designed so the outboard leading edges flex up and back when loaded. The flexing of the outboard section of the wing also allows load relief because the tips increase twist and decrease AOA. The greater the weight, the greater the flex in wing twist. This flexing allows the WSC aircraft to automatically reduce loads in unstable air, providing a smoother ride than a rigid wing. Since the wing flexes and reduces the load for a given angle of attack at the root chord, WSC aircraft cannot obtain loads as high as those obtained by a rigid wing. This flexing of the outboard leading edges also assists in initiating a turn. Second, the wing is designed to flex as it changes twist from side to side for turning, historically known as wing warping. WSC wing warping is similar to what the Wright brothers did on their early aircraft, but they did it with wires warping the wing. The WSC aircraft uses no wires and warps the wing by shifting the weight, which is covered in Chapter 3, Components and Systems. This flexibility is designed into the wing primarily for turning the aircraft without any movable control surfaces like the ailerons and rudder on an airplane. End of page 2-6. Forces in flight. The four forces that affect WSC flight are thrust, drag, lift, and weight. Figure 2.12. In level, steady WSC flight, 1. The sum of all upward forces equals the sum of all downward forces. 2. The sum of all forward forces equals the sum of all backward forces. 3. The sum of all moments equals 0. Note that the lift and weight forces are much greater than the thrust and drag forces. A typical example for many WSC aircraft is that the lift/weight forces are 5 times the thrust/drag forces. Thrust, the forward force produced by a power plant/propeller as it forces a mass of air to the rear, usually acts parallel to the longitudinal axis, relative wind, and flight path. Drag, the aerodynamic force acting on the wing and carriage in the same plane and in the same direction as the relative wind. Lift, the aerodynamic force caused by air flowing over the wing that is perpendicular to the relative wind. Weight, the force of gravity acting upon a body straight down and perpendicular to the earth. During level flight, these forces are all horizontal and vertical. During descents or climbing, these forces must be broken down into components for analysis. Dynamic pressure, Q. Both lift and drag are a direct result of the dynamic pressure of the air. Dynamic pressure, Q, is created from the velocity of the air and the air density. An increase in velocity has a dramatic effect on dynamic pressure, Q, because it increases with the square of the velocity. Doubling the velocity means Q increases by 4 times. Increasing the velocity by a factor of 3 means that the dynamic pressure, Q, increases by a factor of 9. This is a very important concept in understanding the aerodynamics of WSC. Formula for dynamic pressure, Q equals V2x rho/2. V equals velocity. Rho equals density factor. Lift. Lift opposes the downward force of weight and is produced by the dynamic effects of the surrounding airstream acting on the wing. Lift acts perpendicular to the flight path through the wing's center of lift. There is a mathematical relationship for lift which varies with dynamic pressure, Q, AOA, and the size of the wing. In the lift equation, these factors correspond to the terms Q, coefficient of lift, CL, and wing surface area. The relationship is expressed in Figure 2.13. Figure 2.13 shows that for lift to increase, one or more of the factors on the other side of the equation must increase. Generally, the lift needed is about the same for most flight situations. A slower speed requires a higher AOA to produce the same amount of lift. A faster speed requires a lower AOA to produce the same amount of lift. End of page 2 to 7. Because lift is a function of dynamic pressure, Q, it is proportional to the square of the airspeed, therefore, small changes in airspeed create larger changes in lift. Likewise, if other factors remain the same while the CL increases, lift also increases. The CL goes up as the AOA is increased. As air density increases, lift increases. However, a pilot is usually more concerned with how lift is diminished by reductions in air density on a hot day, or if operating at higher altitudes. All wings produce lift in two ways. 1. Airfoil shape creates a higher velocity over the top of the wing and a lower velocity over the bottom of the wing with Bernoulli's Venturi effect. 2. Downward deflection of airflow because of the curvature of the wing with the principle of Newton's third law of motion. For every action, there is an equal and opposite reaction. Both principles determine the lifting force. Review the pilot's Handbook of Aeronautical Knowledge to understand Newton's laws of motion and Bernoulli's Venturi effect. Figure 2.14, top, shows the amount of lift produced along the wing for an airplane wing with an elliptical planform. Notice how the amount of lift generated is smallest at the tips and increases slightly towards the root of the wing. This is known as the elliptical lift distribution. The WSC wing lift distribution is different because the wing twist at the root is at a higher AOA than the tips. Most of the lift is produced at the center of the wing with less lift produced at the tips. The WSC lift distribution is compared to the lift distribution for an optimum design elliptical wing in Figure 2.14. Drag. Drag is the resistance to forward motion through the air and is parallel to the relative wind. Aerodynamic drag comes in two forms. 1. Induced drag, a result of the wing producing lift. 2. Parasite drag, resistance to the airflow from the carriage, its occupants, wires, the wing, interference drag from objects in the airstream, and skin friction drag of the wing. Induced drag is the result of lift, and its amount varies as discussed above for lift. Induced drag creates organized circular vortices off the wingtips that generally track down and out from each wingtip. Refer to the Pilot's Handbook of Aeronautical Knowledge for additional discussion on wingtip vortices formation. These wingtip vortex formations are typical for all aircraft that use wings, including WSC, PPC, helicopters, sailplanes, and all fixed-wing airplanes. The bigger and heavier the aircraft, the greater and more powerful the wingtip vortices are. This organized swirling turbulence is an important factor to understand and avoid for flight safety. Refer to the Aeronautical Information Manual, AIM, or the Pilot's Handbook of Aeronautical Knowledge, FAA-H-8083-5, for additional discussion. Parasite drag is caused by the friction of air moving over all the components of the aircraft. Just as with lift, parasite drag increases as the surface area of the aircraft increases, and dramatically increases as airspeed increases, the square of the velocity. Therefore, doubling the airspeed quadruples parasite drag. Figure 2.15. The WSC aircraft can be designed for the purpose of being a slow-flying aircraft with a large wing where drag is not a major concern, or can be designed to be a fast-flying aircraft with a small wing where drag is more of a concern. End of page 2 to 8. The aircraft has plenty of items, area, for the wind to strike, including wing, wires, struts, pilot, carriage, engine, wheels, tubes, fuel tanks, etc. Parasitic drag can be reduced by streamlining the items. Round tubes can be streamlined, reducing the drag to 1/3, and cowlings can be used to streamline the pilot and the carriage completely, but not without the additional expense and additional weight of the streamlining. Streamlining does make a noticeable difference in the speed and gas mileage of the WSC, especially for the faster aircraft. Figure 2.16. With the large speed range of WSC aircraft, weight, complexity, amount and expense of streamlining and resultant drag reduction are determined by the specific mission for the aircraft and the manufacturer's make and model. Figure 2.17. Total drag is the combination of parasite and induced drag. Total drag equals parasitic drag plus induced drag. To help explain the force of drag, the mathematical equation D equals CDXQXS is used. The formula for drag is the same as the formula for lift, except the CD is used instead of the CL. In this equation, drag, D, is the product of the coefficient of drag, CD, dynamic pressure, Q, determined by the velocity squared times the air density factor, and surface area, S, of the carriage and wing. The overall drag coefficient is the ratio of drag pressure to dynamic pressure. Induced and parasitic drag have opposite effects as AOA decreases and speed increases. Note the total drag in Figure 2.18. It is high at the slowest airspeeds at high angles of attack near the stall, decreases to the lowest at the most efficient airspeed, and then progressively increases as the speed increases. The WSC wing can fly with a large range of airspeeds. Generally, the most efficient speed is at the lowest total drag, providing the best rate of climb, glide ratio, and cruise economy. However, slower speeds provide higher angles of climb, and faster speeds provide quicker transportation. Figure 2.18. End of page 2 to 9. Weight. Weight is a measure of the force of gravity acting upon the mass of the WSC aircraft. Weight consists of everything directly associated with the WSC aircraft in flight, the combined load of the total WSC aircraft, wing, wires, engine, carriage, fuel, oil, people, clothing, helmets, baggage, charts, books, checklists, pencils, handheld global positioning system, GPS, spare clothes, suitcase, etc. During gliding flight, weight is broken down into two components. The component that opposes the lift, acting perpendicular to flight/glide path, and the component that opposes the drag and acts in the direction of the flight/glide path. During gliding flight, this component of weight is the weight component providing the forward force, which some call thrust for gliding flight. During gliding, straight, and descending in unaccelerated flight, lift, L, and drag, D, components equals resultant force, RF, equals weight, W. Total drag, DT, equals weight component, WD, in the direction of flight. Lift, GL, equals weight component, WL, that opposes lift. Similar to airplanes, gliders, and PPC during gliding flight, less lift is required because the resultant force composed of lift and drag provides the force to lift the weight. In other words, in gliding flight, drag helps support the weight. Figure 2.19. Thrust. At a constant airspeed, the amount of thrust determines whether an aircraft climbs, flies level, or descends. With the engine idle or shut off, a pilot is descending or gliding down. Maintaining a constant airspeed, when enough thrust is added to produce level flight, the relative wind stream becomes horizontal with the Earth and the AOA remains about the same. As described for the airplane in the Pilot's Handbook of Aeronautical Knowledge, thrust equals total drag for level flight. Figure 2.20. When in straight and level, unaccelerated flight, lift, L, equals weight, W. Thrust equals total drag, DT. At a constant airspeed, when excess thrust is added to produce climbing flight, the relative airstream becomes an inclined plane leading upward while AOA remains about the same. The excess thrust determines the climb rate and climb angle of the flight path. Figure 2.21. When in straight and climbing, unaccelerated flight, lift, GL, equals component of weight that opposes lift. Weight, W, equals resultant force, FR, of lift, L, and excess thrust to climb, T. Thrust equals total drag, DT, plus rearward component of weight. End of page 2 to 10. Thrust required for increases in speed. Above the lowest total drag airspeed, Figure 2.18. Faster speeds, lower angles of attack, for level and climbing flight requires greater thrust because of the increased drag created from the faster speeds. AOA is the primary control of increasing and decreasing speeds, and increasing thrust generally does not produce higher speeds, but additional thrust is required to maintain level flight at higher speeds. Ground effect. Ground effect is when the wing is flying close to the ground and there is interference of the ground with the airflow patterns created by the wing. At the same angle of attack, lift increases slightly and the drag decreases significantly. The most apparent indication from ground effect is the unexpected lift given to an aircraft as it flies close to the ground, normally during takeoffs and landings. More details for ground effect aerodynamics are found in the Pilot's Handbook of Aeronautical Knowledge. Flight characteristics for ground effect are covered in the takeoff and landing chapters. Center of gravity, CG. The CG is the theoretical point of concentrated weight of the aircraft. It is the point within the WSC aircraft about which all the moments trying to rotate it during flight are balanced. The most obvious difference in the CG for a WSC aircraft is the vertical position compared to an airplane, as it is always lower than the wing. The Pilot's Handbook of Aeronautical Knowledge accurately states the CG is generally in the vertical center of the fuselage. The same is true for the WSC aircraft. However, the WSC wing is higher above the fuselage/carriage and, since most of the weight is centered in the carriage, the CG is well below the wing. In a two-seat WSC aircraft, the second seat is typically behind the pilot's seat and the CG is usually located close to the rear passenger seat. Therefore, the CG location does not change significantly with a passenger. Fuel tanks are typically located near the vertical CG, so any difference in fuel quantity does not significantly change the CG fore and aft with different fuel quantities. For level flight, the CG is directly below the wing/carriage attachment point known as the hang point, and the propeller thrust line is typically designed to be near the vertical position of the CG. Figure 2.22. End of page 2 to 11. Axes of rotation. The three axes of rotation intersect at the CG. Figure 2.23. Lateral axis, pitch. Motion about the lateral axis, or pitch, is controlled by AOA/speed and the throttle. Lowering the AOA, increasing speed, rotates the nose down, while increasing the AOA, decreasing speed, rotates the nose up. Increasing the thrust of the propeller rotates the WSC aircraft pitch up, nose up, to climb and pitch down, nose down, at reduced throttle. End of page 2 to 12. Longitudinal axis roll. Turning is initiated by rolling about the longitudinal axis into a bank similar to an airplane using aileron and rudder control. To turn, shift the weight to the side in the direction of the turn, increasing the weight on that side. This increases the twist on that side while decreasing the twist on the other side, similar to actuating the ailerons on an airplane. The increased twist on the side with the increased weight reduces the AOA on the tip, reducing the lift on that side and dropping the wing into a bank. The other wing, away from which the weight has been shifted, decreases twist. The AOA increases, increasing the lift on that wing and thereby raising it. Thus, shifting the weight to one side warps the wing, changes the twist, to drop one wing and raise the other, rolling the WSC aircraft about the longitudinal axis. Figure 2.24. More details on the controls that assist wing warping are covered in Chapter 3, which should be considered with use of the controls in the takeoff, landing, and flight maneuvers sections of this handbook. Vertical axis, yaw. The WSC wing is designed to fly directly into the relative wind because it does not provide for direct control of rotation about the vertical axis. Stability and moments. A body that rotates freely turns about its CG. In aerodynamic terms for a WSC aircraft, the mathematical value of a moment is the product of the force times the distance from the CG, moment arm, at which the force is applied. Typical airplane wings generally pitch nose down or roll forward and follow the curvature of the upper airfoil camber, creating a negative pitching moment. One of the reasons airplanes have tails is to create a downward force at the rear of the aircraft to maintain stabilized flight, as explained in greater detail in the Pilot's Handbook of Aeronautical Knowledge. The WSC wing is completely different and does not need a tail because of two specific design differences: a completely different airfoil design creating a more stable airfoil and lifting surfaces fore and aft of the CG, similar to the airplane canard design. WSC unique airfoil and wing design. As shown in Figure 2.2. The WSC airfoil has the high point significantly farther forward than does the typical airplane airfoil. This makes the center of lift for the airfoil farther forward and creates a neutral or positive pitching moment for the airfoil. Most WSC airfoils have this unique design to minimize negative moments or pitch down during flight. Additionally, the design of the complete wing is a unique feature that provides stability without a tail. To understand the WSC aircraft pitch stability and moments, examine the wing as two separate components: root chord and tip chord. Trim, normal stabilized flight. In Figure 2, 25A. During normal unaccelerated flight at trim speed, the lift at the root, LR, times the arm to the root, AR, equals the lift of the tip, LT, times the arm to the tip, AT. LRXAR plus LTXAT equals 0. LR plus LT equals total lift of the wing, LW. Adding all the lift from the wing puts the center of lift of the wing, CLW, directly over the CG for stabilized flight. Figure 2, 25A. If the pilot wishes to increase the trim speed, the CG is moved forward. This is done by moving the hang point forward on the wing. Similarly, to reduce the trim speed, the hang point/CG is moved rearward on the wing. High angles of attack. In Figure 2, 25B, if the wing AOA is raised to the point of minimum controlled airspeed at which the wing begins to stall towards the center of the wing, root area, the lift in this area decreases dramatically. The CLW moves back a distance creating a moment to lower the nose. Therefore, the center of lift moves behind the CG at higher angles of attack, creating a nose-down stabilizing moment. The average lift coefficient versus AOA is shown for this minimum controlled airspeed in Figure 2, 26. The root area is partially stalled and the tips are still flying. End of page 2 to 13.